In our last lesson, we focused on how to tell whether a reaction is exothermic or endothermic by looking at its temperature changes and thinking about bond energies. Now that we understand what delta H means, we're ready to use it in the same way we use balanced chemical equations, almost like a conversion factor. This is where thermochemistry gets really fun, because heat becomes something we can calculate, just like moles, grams, or number of molecules. Today we'll learn how to read thermochemical equations and use them to solve problems. You already know all of the stoichiometry, we're just adding some heat into the mix. So something that will really help you with these calculations is to think about the fact that the units for the heat of reaction are typically kilojoules per mole, and to recall that heat is an extensive property. So we could write a thermochemical equation, such as this one shown here, where we have sodium metal reacting with liquid water to form hydrogen gas and sodium hydroxide plus heat. So I have two examples here where we're going to look at how the amount of heat involved depends on the amount of reactants that you use. So in this first video, we have 0.15 grams of sodium, roundabout. I had to estimate it. And so we drop the sodium into the water, and you can see it's kind of moving around because it's generating all that hydrogen gas. It's generating so much heat that it actually ignites the hydrogen gas, and you end up getting a characteristic yellow color that indicates that you have ionized sodium being present because of all of the heat. In the next one, we're actually going to take a kilogram of sodium metal. So the way they set up the experiment was they had a bin containing water, and then they taped 1 kilogram of sodium metal to the lid of the bin so that when they tipped it over, the bin with the lid on it, it would cause the sodium and the water to start reacting. So they're doing a countdown, and they tip it over, and you can see we have a much more exciting reaction. So we had a lot more heat generated. So here's an example of that one. We're only going to use 1/10 of a gram, and we're going to look at how much heat, or what the heat reaction actually is for this. So we have 0.1 gram of sodium metal is added to 100 grams of water. The reaction produces sodium hydroxide and hydrogen gas, as we saw. Calculate the molar heat of reaction if the water's temperature increased by 2 degrees C. So first step is always to write out a balanced chemical reaction equation. Now, since we have amounts of both the sodium and the water, we're going to determine the limiting reagent. You can probably guess that the sodium is going to be the limiting reagent because it's there in such a small amount. So we set up a chart. We find out that we have 0.0043 moles of sodium present and 5.55 moles of water. So you do the stoichiometry, and I'm going to go over to hydrogen because it has a coefficient of 1. That way I know that whatever heat I end up talking about is on a per mole basis. If you try doing it by the amount of sodium used or the amount of sodium hydroxide formed, that would be on a for every 2 moles basis. Anyway, so we have a 2 to 1 relationship. So we're going to divide that by 2. And then this one is also a 2 to 1 relationship. So we end up with 0.00215 moles of hydrogen gas are formed if all of the sodium reacts and it's the limiting reagent, which it is. So we've settled that part. So now we go on to the next. Oh dear, I got something out of my click sequence is out of whack. That's okay. So the next one, we want to determine the amount of heat involved in the reaction. Remember, we already know what the temperature change is, but that doesn't mean that we know what the heat is, because heat and temperature are two different things. So we're going to use the Q equals mCpΔT. Make sure we use all the values for water. So we write them down again, just to make sure they're all in one place. Plug them into the equation, and we calculate that there should be 837 joules involved if that water is going to warm up by 2 degrees C. So that means that the amount of heat given off by the reaction is going to be a negative 837 joules. Remember, if you are losing heat, you're going to have that negative sign on there. So now we're going to calculate our molar heat of reaction. Remember, it's kilojoules per mole. So we take our joules, we divide by that, divide by the number of moles of hydrogen that are produced. It gives us this really large number, which is why enthalpy is usually, almost always, as far as I can remember, in kilojoules, which converts to that the heat of this particular reaction is negative 389 kilojoules for every mole of hydrogen produced. So just like a balanced reaction equation tells us how many moles of CO2 can form from 1 mole of CH4 in a combustion reaction of methane, delta H value tells us how much heat is involved for that same amount. So in the stoichiometry problem, delta H becomes another ratio that we can multiply by. This is the missing piece that connects energy to mass and moles. So here I have a little picture. We have kind of a Susian convertomatic, and so we put our grams into one side, and it does all of the mathematical conversions, and we have the amount of heat being produced on the other side, or being absorbed. It's not necessarily just for an exothermic reaction. Now the reaction comes up. So in this case, the combustion of methane, we would have 802 kilojoules per mole of methane produced. So now we're going to use that particular reaction equation. It says how much heat is given off when 1.6 grams of methane are burned in an excess of oxygen. So we don't have to worry about whether there's a limiting reagent or not, because we have all the oxygen we need. If the molar heat of combustion, ignore that extra line, is minus 802 kilojoules per mole. So as ever, write out the reaction equation. Calculate the number of moles that are involved. So we have 0.1 moles of methane are being combusted. Calculate the amount of heat given off. So there's actually two ways to do this. So you can say, all right, well, I know it's kilojoules per mole. So if I multiply by the moles will cancel out. That's sort of a dimensional analysis approach. And you get negative 80.2 kilojoules. On the other hand, you could also set up a proportion where we have, we know that it's negative 802 kilojoules for every 1 mole. And so you are just determining how much heat is involved if you only have a tenth of a mole. So it's a tenth as much. So just kind of building in a question here, is this going to be an exothermic or an endothermic reaction? My students have pointed out that there's 3 different ways to figure this out. You can either say, well, I know it's exothermic because it says that heat is given off. Or you could say, well, I know that is a combustion reaction, so therefore it's an exothermic reaction. And the third way, which most of them don't suggest at this point, is to point out the fact that we have a negative delta H value, which means it is exothermic. So 3 different ways to get the same answer. All right, so another question, kind of slightly, or another example, sort of a slightly different approach. It says, what is the molar heat of combustion of propene? So that's C3H6, it has 1 double bond in it, if you feel like drawing it. If burning 3.2 grams of propene releases 156 kilojoules of heat. So again, write out the reaction equation. Convert the grams of propene to moles. So we have 3.2 grams of propene, which means it's 0.076 moles of propene. Divide the heat produced by the moles of propene involved. And so it ends up being, so we have negative 156 kilojoules over the number of moles, and you end up with a molar heat of combustion of negative 2,053 kilojoules per mole. So in that case, the part that was different is we were finding the molar heat of combustion, whereas in the previous example, we were given the molar heat of combustion and we were using it to figure out how much heat would be released. All right, so the wrap up. It's a pretty short lesson. Delta H tells us the heat change for a reaction as written. This is where you have to pay attention to the coefficients on the different parts. So in that first reaction, when I was talking about the reaction between sodium metal and water, I did it in terms of the hydrogen gas because that made it the simplest possible. If I had done it in terms of the number of moles of sodium, I would have to include that factor of 2. The amount of heat involved scales with the amounts used in the reaction because heat is an extensive property. So the more reactants you use, the more heat you're going to generate. As long as you're increasing both reactants or you have stoichiometric amounts of everything present. If you have 0.1 grams of sodium metal and you're increasing the amount of water, that's not going to change the amount of heat at all because you're limited by how much sodium you have present. So we can use calorimetry, seeing how much water warms up by, to determine molar enthalpy. So that's where you measure the change in temperature. You calculate the Q that is involved, the amount of heat involved, using the Q equals mCpΔT, and then you divide by your moles, and that will give you your delta H value. And then we can kind of flip it around, and we can use delta H values as a way to convert from grams of a reactant to figure out how many kilojoules of heat will be released or absorbed once the reaction has been completed. So the big idea for this lesson is that energy changes follow mole ratios. So remember, thermochemistry is stoichiometry with heat. So thanks for listening. See you in the next lesson.